So projecting our vectors. Right? So we're saying we can break up our vectors into components, and we like to do that, those components being perpendicular to each other, and for convenience we've said, well, horizontal and vertical, so x-axis and the y-axis. Here's a position vector, length of 2, makes an angle of 30 degrees with x. I can easily draw up a right angled triangle, and with a bit of trig we could see that, oh, the length of that must be 2 cos 30, which is root 3. So I know the horizontal component would be root 3 in the I direction. I could do a similar thing over to the y-axis, and a bit more trig, that'll be 2 cos 60 equals 1, and so the vertical component is just j, and we know we could rewrite our vector in component form. So we could rewrite our vector in component form, root 3i plus j. So horizontal and vertical was nice and convenient because of our coordinate axes, and then we can use coordinate geometry ideas and things like that if we need to. But it doesn't have to be horizontal and vertical. The key is we just want two things that are perpendicular to each other. So say I did something like this. I've got this vector u, and I want to project it onto this other one, v, and it's not horizontal and it's not vertical. How would I do it? Well, how I would do it is I would draw perpendiculars to that vector. Remember, we want them to be at right angles. So if I was to drop down those perpendiculars, here's my new vector in that direction. So that would be the component of the vector in the direction of v. If I create a right angled triangle, so obviously those lines would be parallel, call that theta, and then it would end up being whatever the length of the vector is, so u times cos theta would be the length of that. So that would be also the length of the shadow, if you like. Imagine you had a light behind that vector and it's shining it on. It'd be the length of that shadow. Then to get the direction, well, we now know our new vector's going in the direction of v. So I'd multiply it by, not v though, it'd have to be the unit vector v, otherwise it's going to change the length of that vector. So I need to multiply it by a vector with magnitude 1. So it'd be the unit vector in that v direction. So this would become the new vector. The magnitude of u cos theta, that's its length, times the unit vector, so v with the caret on top. Now let's come up with a nicer formula. Remember we saw this, the dot product. U dot v, magnitude of u, magnitude of v, cosine theta. Playing around with that, remember the length of my new vector was magnitude of u cos theta. So if I play around with that first equation, I get an expression for that. It's u dot v over the magnitude of v. So now I know the projection would be u dot v over the magnitude of v times the unit vector in that direction. Well, the unit vector, we said, was the vector v divided by the magnitude of v. I can tidy this formula up a bit more. I now get u dot v over the magnitude of v squared times v. Now the temptation here is to now cancel, but I can't. I need to leave it like that. Mind you, I find it easier, rather than saying magnitude of v squared, I suppose it's more in my head the way I think about it, is I go, oh, it's u dot v over v dot v times v. I just find that easier to remember. But as I was saying, you can't, because remember, the dot product is not multiplication. So its inverse is not division. I can't cancel this vector v into the magnitude of v squared. They are different terms. One is v, the vector, one is the magnitude of v. They are different. One's a scalar, one's a vector. I can't cancel. And just a couple of ones to, if you're playing around with projections, if you wanted to find the projection of some scalar times u, you could find the projection of u first, then multiply it by the scalar, or multiply it by the scalar first, then find the projection. That doesn't matter. And if you're going to add two vectors together, then find the projection, that would be the same as just projecting each of them individually and then adding that result. All right. Let's do this example then. Make sure you read the question carefully, what they're actually asking for. This one is not actually asking for the projection, it's asking for what's the length of the projection, how long is it? Remember, we created a formula that said this. Originally, when we were finding just the length of that, it turned out to be u dot v over the magnitude of v. Now I've put absolute value or magnitude around the u dot v there. Do I need it? I'm going to get a scalar, but it might be negative. And if I'm talking about the length of something, it's a positive number. So I'll put some absolute value signs around the top as well to ensure I get a positive number for that length. Well, if we sub our one into that formula, a dot b, 5 times 3 plus negative 1 times 4, over the magnitude of b, so it's the magnitude of the one we're projecting it onto. Square root of 3 squared plus 4 squared, we'll get 11 on 5. Another term you might see, they might say, what's the scalar projection? Don't know if I like that wording, but you see it. Basically, it's saying what's the length of the vector projection. All right, let's do an actual projection then. We're going to project the vector 2i minus 5j onto minus 2i plus 3j. So the projection of u onto v. So u dot v, 2 times negative 2 plus negative 5 times 3 over v dot v, which is the magnitude of v squared, so I'll end up with negative 2 squared plus 3 squared. We're also multiplying it by the vector we're projecting it onto, minus 2i plus 3j, and tidying all that up, whether I leave it factorised, whether I expand it out, I mean either are they're the same thing of course, they're just two different ways of writing what that vector would be. Now let's look at something more interesting. Okay, HSC, of course, is 12 months away. Let's see what happened in 2023. This was a very interesting question. You'll notice it's 14C, by the way. Question 14 is the last question in the Extension 1 paper. And C, it's getting towards the very end of the paper. So we're expecting something a little bit more challenging. Given a non-zero vector PQ, it's known that the vector Q negative P would be perpendicular to it and has the same magnitude. Do not prove this. And I put that in there because some people will look at it and go, oh, well, better prove that. No, don't need to. You can take that as fact. We can use it. We've got two vectors, A and B, and they've given us their position vectors. Using that information, or otherwise, if you want to, try and do it another way, by all means do it. But hey, I'm giving you a big hint that this is probably the easiest way of getting the answer. Show that the area of that triangle is, well, a half times the magnitude of A1B2 minus A2B1. I like to draw diagrams for things like this so I can get my head around the problem. So I've got these two vectors, it's going to create a triangle if I draw in that third side. Okay, I've got to find the area of this triangle, by the way. And I know two ways of finding the area of a triangle. One is half base times height, and the other, of course, is half AB sine theta. Well, it looks like I'm going to go half base times height, given the information I've been given. All right, so how do I get the perpendicular height? I just got to choose one of these sides to be the base of the triangle. Got to find the perpendicular height. If I construct this other vector, because see, they've given me a clue here, talking about perpendicular. So I want another vector that's perpendicular to one of these vectors in the triangle. So I can create a perpendicular height. I've chosen to go perpendicular to B. So here's my third vector, well, fourth if you include the side of a triangle, but here's my third vector, and they've told me that if my original vector was PQ, the one that's perpendicular to it would be Q minus P. So my original vector was B1, B2, so this one here that I've constructed must be B2 minus B1. Okay. Now, yes, so from the information then, that's the vector that is perpendicular. I know that's perpendicular. If I now project OA onto OC, I'm going to create this new vector down here, OX. Why do that? Because if I slide that vector into place, it becomes the perpendicular height of the triangle. So now essentially I need to find the length of this vector that I've projected onto OC. And that will tell me the perpendicular height of that triangle. So the area of my triangle will be the length of the vector OB times the length of the vector OX that I created. Well, half of that, because we're talking about the area. So half the magnitude of OB times magnitude of OX. OB, well, we know that one, they gave us the coordinates. OX, I've got to work out. That was the projection of OA onto OC. but it's just the length I'm interested in. So it'll be the magnitude of the dot product, OA/OC, divided by the magnitude of OC, the vector I'm projecting it onto. OB and OC are the same length. All we said was, it's known that the vector has the same magnitude. So that new one I created has the same magnitude as B. So OB and OC, same magnitude, which means they cancel out. So all I now need is the magnitude of the dot product OA/OC. Well, we know the vectors for those. OA, they told me was A1, A2. OC, the one we created, B2 minus B1. Let's do the dot product of that, and we get half of A1 B2 minus A2 B1. All right, but there was a part B to this. That was just part A. So you can get that nice little formula which you're going to use in this part here. So P's on the right hand circle, centre little r0, and Q is on the left hand circle with centre negative big R0. And what else have we been told? So the angles for the first vector, or the angle in the first circle is T, and the second circle 2T. Note, so they're giving us a hint here, OP, by the way, would be the same as writing OI plus IP. Smash them together, and OQ, OJ plus JQ. Not an amazing piece of information, but at least it gives you a clue as to how to approach the problem. Using the first part, or otherwise, by all means, if you want to go a different way, find the values of T, restricting T in between minus pi and pi, that maximises the area of this triangle. Now, I'll now pre-warn you. To do the solution to this, I have to use something we haven't actually looked at yet, and that's how to differentiate trig functions. So you just have to take me at face value that when I do that derivative, they are the correct derivatives. But obviously by the time we do the HSC, we'd know that. Let's get expressions for our two vectors. So OP is any point on this circle. And if you remember the parametrics of a circle, the radius cos theta, radius sine theta, but we've got a circle shifted, so my x coordinate will actually be r plus r cos t on that right hand circle. On the left hand circle, we've shifted it the other way, capital R, so I'll get minus capital R plus capital R cos 2t for the x value, and the y value will be capital R sine 2t. There's my two vectors. We just found a formula for the area of the triangle. So I'll just substitute that information in, and we have this expression. But I can play with this, because I'm going to rewrite it now. If I expand these parentheses out, actually the first thing I did is took out the common factor of little r capital R. It's in everything, so let's just pull it out and get left with this trig expression. Now when I expand the parentheses out, I'll get sine 2t plus sine 2t cos t minus cos 2t sine t. Hello, that's familiar. And then a plus sine t at the end. Sine cos cos sine. That's the sine of 2t minus t, which is of course sine t, so I've actually got 2 sine t. Here's now my expression. Remember, we're trying to maximise that area. R is a constant, capital R is a constant. The only thing that's going to change the area is what's inside the magnitude there. So that function itself is what I'm trying to maximise. And when we're looking at curves, we know that the maximums, or minimums for that matter, will happen at the turning points or stationary points. So it'll be when the derivative is equal to 0. The derivative for this function turns out to be 2 cos 2t plus 2 cos t. So we go and work out that derivative, and we're saying, hey, I want to know when is that equal to 0. I now have a trig equation to solve. 2 cos 2t plus 2 cos t is equal to 0. Remember, we're going in between minus pi and pi. Okay, let's turn it into a quadratic. I'll now change cos 2t to be 2 cos squared minus 1, and I've got a nice quadratic there. What multiplies together to give negative 1, adds together to give positive 1. We've got a factorisation. So either cos t equals a half or cos t equals negative 1. Well, cos t equals a half, given the restriction on the domain that I've got, I'll get two answers. plus or minus pi on 3. The other one, cos t equals -1, I'll get plus or minus pi. Look at the diagram they gave me. If t was plus or minus pi, they're not going to be solutions because you're not going to get a triangle because the points would end up being collinear. So the only possible solutions are plus or minus pi on 3 for that one. There's a few little places you could fall in the traps there, not spotting that last bit about, hang on, discounting those solutions and so on. All right, 8E.